our experiment is going to be this. We're going to have 1.4 times 10 to the minus 6 grams of zinc carbonate, or ZnCO3, is going to dissolve in 1 milliliter, or we'll say 1.000 milliliters of solution. It's also found that 2.8 times 10 to the minus 6 grams of barium chromate, which is BaCrO4, dissolves in 1.000 milliliters of solution. And we're going to assume that these solutions are aqueous. What we want to do here is calculate the KSP for both. So in order to calculate the KSP, we're going to form these saturated solutions. So the first thing that we want to do in every case, when I'm thinking these problems through in my mind, the first thing that I see is an equilibrium expression. So the equilibrium expression that we're going to write, first is we're going to look at the zinc carbonate, which is ZnCO3. It's going to be in equilibrium with zinc 2 plus ions plus CO3 2 minus ions. What we can say is that the KSP for this particular expression is going to be the concentration of zinc 2 plus times the concentration of CO3 2 minus. These concentrations are in units of moles per liter, which we abbreviate and can say molarity. So we have grams per milliliter, and we need to convert that over to moles per liter. So if we have 1.4 times 10 to the minus 6 grams of zinc carbonate per milliliter, we can set up a conversion factor, and we know that 1 mole of zinc carbonate is 125.39 grams. We can get that by looking at the periodic table. We also know that 1 mole of zinc carbonate, or for every 1 mole of zinc carbonate that dissolves, we're going to get 1 mole of zinc 2 plus in solution. And we also have to use the conversion, or when we calculate this out, we can cancel out grams, and we can cancel out moles of zinc carbonate. So we have moles of zinc 2 plus. We also need to convert over to liters by using the milliliter to liter conversion, and this gives us 1.1 times 10 to the minus 5 molar. So this right here is our concentration of zinc 2 plus in solution. We can also look at this equilibrium expression. For every 1 mole of zinc 2 plus that we have in solution, we have 1 mole of CO3 2 minus in solution. So if this is 1.1 times 10 to the minus 5 moles of zinc 2 plus per liter, we know from our balanced equilibrium expression that for every 1 mole of zinc 2 plus, we get 1 mole of CO3 2 minus, which tells us that 1.1 times 10 to the minus 5 molar is also the concentration of the CO3 2 minus. So the KSP is going to be equal to the concentration of 1.1 times 10 to the minus 5, that quantity squared, which equals 1.2 times 10 to the minus 10th. One thing that I would mention about this value, whenever you calculate a numerical value in the lab, you want to think about it. And you want to think about what that value means. Here, we're given a very, very, very small value for K. So what that's telling us is, that's telling us that the equilibrium is going to lie over to the left. And there's going to be a lot of solid present. So when you take this zinc carbonate and you try to dump it into a solution, not very much of it's going to dissolve. Okay? If you look in Chemistry 121 in Chapter 4, the solubility rules are going to tell you that this is going to be insoluble. To the naked eye, it might be insoluble because there's only going to be 1.4 times 10 to the minus 6 grams that dissolve per milliliter. 1.6 times 10 to the minus, or 1.4 times 10 to the minus 6 grams, that's really, really hard to measure. If you think of the balances that we have in our balance room, they don't measure out that far. So to the naked eye, you might not be able to see much of this dissolve, but if we have enough, complex equipment, we can try to figure this out. We can do the same type of calculation for the barium chromate. And what we're going to do with the barium chromate is take 2.8 times 10 to the minus 6 grams of BaCrO4. And that's going to be per milliliter. We know that 1 mole of barium chromate is going to have a molecular mass or a molecular weight of 253.3 grams. For every 1 mole of BaCrO4, there's 1 mole of barium 2 plus. This gives us moles of barium 2 plus per milliliter. We need to convert to liters to get our molarity units. And we also get 1.1 times 10 to the minus 5 molar. If we look at our equilibrium expression, it's going to be barium chromate in equilibrium with barium 2 plus CrO4 2 minus. So the concentration of barium 2 plus is going to equal the concentration of CrO4 2 minus, which they both equal 1.1 times 10 to the minus 5. The KSP is going to equal 1.1 times 10 to the minus 5, that quantity squared, which is going to equal 1.2 times 10 to the minus 10.